All right, everyone, our homework that we had last night, page 63, 2 to 16, and we got a number of questions that we need to go over here, starting with question number 5. Question number 5 says, a rock takes 1.575 seconds to drop 2 meters down toward the surface of the moon. What's the acceleration due to gravity on the moon? So a little bit of a different question in that in all these gravity questions to this point, we've been solving for A. We've had the value of A, and we've been solving for the value of something else. This time, we're solving for the value of A, the acceleration due to gravity on the moon, which we know is going to be different than 9.81 or negative 9.81 meters per second squared. Okay, what do we got here? We got a time here that it takes the rock to fall, 1.575 seconds. We have a displacement of the rock. It's 2.00 meters. We don't have the acceleration. In fact, that's what we want. Is there anything else we have? Anything else that we have if we read between the lines a little bit? Yeah, it's dropped. VI is equal to 0 meters per second. So it's a group B problem, obviously. They have all been for a while now. But what equation within group B, which of those 5 are we going to try first for this? Can't come up with one in 30 seconds or so? Just give me one. Just give me one. I don't care if it's the right one. If it's a group B equation, it's not the wrong one. Yep. Yes, that's a good point, actually. Sometimes I make those mistakes on purpose. This time I did not. That should be a negative. You're right. See, everybody can make a silly mistake, right? It's not the end of the world. You got to try them, right? Okay, so what do you want to try here? Yep. Good. D is equal to VIT plus 1/2 AT squared. They're all valid, but this is the one that's going to get me the answer the quickest, right? Solving for A here. Get rid of what's not connected first. What's not connected to the A. What variable or variables are not connected to the A? T. Yep, VIT. Good. So how do we get rid of that? VIT is added to 1/2 AT squared. How do we get rid of it, Bree? Oh, you're right, actually. Yeah, good point. Now, Joseph, you're right. It's that is what we would get rid of, and we'd take it over by subtracting. Except that in this case, it's easier just to get rid of it because its value is 0, right? Okay, so this becomes easier actually. We got to get rid of the 1/2 and the t squared. They're both multiplied by A, so how are we going to get rid of them? By dividing. Good. So let's say D divided by 1/2 t squared equals A. So it becomes negative 2.00 over 1/2 of 1.575 squared. I don't know what the answer is here, and I can't do this one in my head, but I know what the gravity is of the moon. It's somewhere around 1.6. What do you get for that? Yeah, it should be negative, yeah, because it's an acceleration due to gravity. 1.6, let's go to 3 digits. 1.60, 1.61. Right, 3 digits, because if we look at this, 4 digits, 3 digits, remember, our final answer is rounded to basically the weakest data point, the weakest piece of data. The weakest piece of data is 3 digits there. Is that okay? Question number 9 is next. It says, if a baseball popped straight up into the air as a hang time, which they tell us, they define hang time for us in case we're not familiar with baseball or football, the length of time in the air of 6.25 seconds, what's the distance from the point of contact to the baseball's maximum height? That's a good question, actually. That's a good question. What do we have given to us here? What do we have given to us? Yep. Time. Good. What's the time? Okay. What else do we have given to us? What's the final velocity? No. Oh, okay. So you're not analyzing the hang time. You're analyzing only the trip up. Okay. Wait a second then. If you're saying VF is equal to 0 and you're analyzing only the trip up, then what's the time? We're going to divide that time by 2, right? So it's going to be 3.125. That makes sense, Chantal? Yeah. So the total time is 6 seconds, but if we're only looking at the trip up, which Nathan's suggesting here, then we're going to cut it in half. I think that's the way to go, too. A is negative 9.81, right? And we're looking for the displacement, not the total displacement of the baseball, because the total displacement is 0. It goes up and it comes back down where it started. But its displacement at maximum height when VF is 0 is what we're looking for here. Let's try this one. D is equal to VFT minus 1/2 AT squared. We don't use this one very often. VF is 0. So we're going to say what's negative 1/2 of negative 9.81 times 3.125 squared. We don't see a lot of multiple choice questions in Physics 20, but we do in Physics 30. Okay, if this was a multiple choice question in Physics 30, I promise you this. If you forget to divide the time by 2, you go 6.25 seconds, guess what? That option's going to be there. Okay, that option's going to be there. So don't forget little things like that. Dividing by 2. What do we end up getting for the displacement there? Positive, right? Negative times a negative is a positive. Positive what? $47.9. Anyone else? Yes? All right, we're going to round that to 3 digits. We round it to our least precise piece of data or our weakest piece of data. And there's only one piece there, so besides the 9.81, so it's 3 digits. Good. Number 10, jumping straight up, how long will a red kangaroo remain in the air if it jumps through a height of 3 meters? You ever wonder sometimes when you're reading these questions, like, where this comes from? Like, who came up with the idea of, and jumping a red kangaroo? I didn't even know there were red kangaroos. Anyways, it doesn't matter what the context is. In the end, whether it's a red kangaroo or a whatever, a buffalo jumping, I don't know if buffalo can jump 3 meters in the air, but the question is the same question, right? We're looking for the time. How long will it remain in the air? We've got A is negative 9.81. The displacement is 3.0 meters. And there is something else that I have here too. The displacement is 3 meters at max height. At max height, what else do we have for read between the lines? Good. It's what is it? Good. VF is 0. All right, so A, D, VF, T. Let's use this one again. Same one we just used. This disappears because VF is 0, 0 times time is 0. We're solving for, no, we're solving for, what are we solving for? T. Solving for T. So let's take the half A over by 1/2 A goes over by doing what? Dividing, yeah, dividing. So we'll say D over a half A. It's multiplied by T squared, right? So get rid of it by dividing. And now we're going to square root that. So it becomes 3.0 over 1/2 of, wait a second. Wait a second. What's wrong with this? Get the negative on the 1? Oh, that's it, yeah. Why was I puzzled there? Bree pointed out that I forgot the negative on the half. Why was that a big deal? Tasia, why was that a big deal? Yeah, I was looking at that and thinking, I can't take the square root of a negative number. I've missed something. Okay? Listen, when something like that pops up, mathematics is like whether you like math or not, math is elegant. Like things like that don't happen. Like if you put numbers into an equation and you do it properly, you will never have to take the square root of a negative number. If you do, you've made a mistake. Okay? And I knew I made a mistake there. I just took Bree to figure out what that mistake was. So it is negative 1/2 a. So it's negative 1/2 times negative 9.81. Now I have the positive inside the square root sign. So what does that work out to be? 3 divided by 4.9, 0.6. Square root of 0.6 is, I don't know, about 0.8, 0.7, 0.8. If nobody's going to tell me, I'm just going to write down a random number there. All right, 12.9 seconds. That's what it is. You have what it is on there? Sorry? 0.78? That sounds about right. Anybody agree with that? Look at that. I see all these heads bobbing. Yeah, I agree with that. Why didn't you tell me in the first place if you had that answer, huh? Yeah. I know that you feel that way. Yeah. Number 12. A coin tossed straight up into the air takes 2.75 seconds to go up and down from its original position. From its initial release point, 1.3 meters above the ground. What's its maximum height? There's a good question. These are getting better and better, or more challenging and more challenging. We got a time here, right? What's the time? Choose wisely. What's the time here? 1.375 seconds. If we're analyzing the trip up, and we're going to analyze the trip up, generally, if you're looking for a maximum height, you're going to analyze the trip up. The F will be equal to 0, just like it was in all the other questions where we're finding max height, right? We have a displacement of 1.3? No, we don't. It doesn't say it moves 1.3. Displacement is its change in position. It just says that it was released 1.3 meters above the ground. It didn't say anything about moving that 1.3. That's what we're going to solve for, you guys. The displacement. We're going to say VFT minus 1/2 AT squared. Remember, you're allowed to try any of them. The F is 0. Nathan, you have the answer for that? Not the final answer, but value for D there. Okay. Anybody have the value for D there? We got 6.74 meters, but that's not my answer. What's my answer? Where do I go from here to get the answer? Oh, we're so close. And you know what? The math here is easy now. Yeah, this is the displacement above where it was released. We're looking for the displacement above the ground. So we have to add to that 1.3 meters. So let's say they gave me 8.04. Oh, is that wrong? 9.27 meters. Okay, so we add that to 1.3, gives us 10.57, which should be rounded to 3 digits, 10.6 meters. 9.27 meters above where it was released, 10.6 meters above the ground. Good? 14. Says a person in an apartment building is 5 meters above a person walking below. She plans to drop some keys to him. He is currently walking directly toward a point below her at 2.75 meters per second. How far away is he if he catches the keys 1.25 meters above the ground? Did anybody look at this question and think, what? This is a hard question. Is there anybody that looked at this question, answered the question, and is relatively confident they have a right answer? Good. Did you check your answer? You did, and you got the right answer? Good for you. This is a hard question. This is a great question, though. Honestly, on a test, you probably wouldn't get something quite this difficult. But it's a great question to go through to exercise the brain. Sometimes when we're practicing for a sport, we challenge ourselves more in practice than we're ever going to see in a game because it makes us stronger and makes us better equipped to deal with the game, right? Sometimes when we're doing practice questions with our mind, we do something harder than we're going to see on an exam because it stretches our mind. It strengthens our mind so that we're better prepared to deal with what we do see on a test here. Question? I don't think that would simplify it. No, I don't think you're simplifying anything at all by calculating the time that it takes to make it to the ground. I thought you were on the right track there for a little while, but I don't think you want to find the time that it takes to reach the ground. I think you'd be doing more work than you have to do there. Because in the end, you want the time that it takes to fall. Let's look at this. Let's draw a picture. Okay, let's draw a picture. Here's the keys. Okay, put me on the spot. It's a key ring, okay? It's a key ring. I'm dropping a key ring. And it's off in the distance, so you can't see it very well, okay? It's 5 meters above the ground, but the guy who's catching it, his hand is 1.25 meters above the ground. The guy's walking this way with a velocity of 2.75 meters per second. We want to know, we want to know how far away he is right here, this distance right here. Anybody have any idea where to start here? Julia? Okay. No, we don't know the displacement of the keys. Okay, so we're not given the displacement of the keys. We have to find the displacement of the keys. Julia, you're right. Now, it's a pretty simple calculation, but it's still a calculation. We're not given that value. The displacement of the keys downward will be negative 3.75 meters. Does that make sense, everyone? Not 5 meters, not 1.25. The displacement of the keys downward will be negative 2.75, 3.75. Why? Because the keys don't have to fall all the way to the ground. They only have to fall to his hand. And his hand is 1.25 meters above the ground. Good? So the keys fall downward 3.75 meters. What else? Anything else? Any other ideas? Joseph? Okay, the initial vertical velocity, the downward velocity is 0. Okay? Anything else? Downward acceleration is neg 9.81 meters per second squared. All right, so let's start writing some things down here. For this part of the question, we're going to say VI is 0. Joseph said it was dropped downward, so VI is 0. A is negative 9.81. Nathan told us it's negative 9.81. Julia told us the displacement is negative 3.75 meters. Okay. What else? Which way is this guy walking? Yeah. You could have drawn walking to the right as well, right? It doesn't really matter. But in my diagram, the reference frame that I have, he's walking to the left, right? That's not up or down. We got to be careful with that. Okay, let's write down two sets of givens here. A set of givens for our up and down motion, and then another set of givens for our horizontal motion. Okay, for that, we have his velocity is 2.75 meters per second. That velocity, horizontal, is independent of this vertical motion. Okay, him walking doesn't affect the keys falling. So we got to consider it as a separate problem. I think that's all we have for the horizontal motion, isn't it? We want to find how far he walks horizontally, right? That's it. That's all we got. Let's do this. Let's analyze the up and down motion because we seem to have more information about that. We have the displacement, we have the acceleration, we have VI. Okay, let's try this. D is equal to VIT plus 1/2 AT squared. Let's see what that gets me. DI is 0, so that disappears. We got D, we got A. Let's solve for T here. The 1/2 A comes over by dividing. And then we're going to square root that to get T. Hey, I'm not looking for T, but I can find it. Maybe that's going to help me. Maybe it's not. But it's something at least. Displacement is negative 3.75 divided by 1/2 of negative 9.81. Can you guys calculate that for me, please? 0.87 seconds. Okay, how is that useful to me? Or is it? For the red one, the horizontal? Yeah, because we have the time. Now listen very carefully. I told you a second ago that the green displacement here is independent of the red. The red velocity is independent of the green. We can't take this velocity and put it over into this vertical problem. We can't take this acceleration and put it into this horizontal problem. So why is it, Tegan, can we take the vertical time and put it into the horizontal equation? Why can I move the time over here? Okay, so why can I do this with time, the time variable, but no other variables here? Because time doesn't have a direction, right? Velocity, displacement, acceleration, they're all vectors. They all have direction. So it's either up or down, or it's horizontal. Time, hey, the time taken, we can switch it back and forth from x to y, from horizontal to vertical, because time's a scalar. All right, so now this is a group A equation right now, or group A problem, because he's just walking at a constant speed. V equals d over t. Rearrange that. D is equal to V times t. V is 2.75 times 0.87. What do we get there? We're going to say 2.4 meters. Rounded to 2 digits, because we look back to our weakest piece of data, 2 digits, 3 digits, 3 digits. Weakest piece of data is 2 digits. Final answer should be 2. Luca got that question. Anybody else? Good, actually. That's not bad. Half a dozen of you got that? That's a tough question. That's a tough question. Anybody kind of feel like they were on the right track and then just kind of messed up kind of near the end or something? Okay, that's a tough question. If you understand that question, I'm not saying if you can do that question. If you understand what we did for that question, that's good. You're smarter now than you were 5 minutes ago, if you understand how to do that question. 15, the last one that we have here, says a rocket launched vertically upward accelerates for 50 seconds until it reaches a velocity of 200 meters per second. Then its fuel runs out. What's the rocket's acceleration? What's the height of the rocket when its fuel burns out? Why will the rocket continue to gain height for 20 seconds? And what's the maximum height of the rocket? I don't think this one's quite as hard, to be honest. I think it's hard. I think it's the second hardest question on the page. Not quite as bad as 14, though. We've got two things happening here. We saw this a little bit yesterday. Two things happening. The rocket is being launched vertically upward. It's accelerating upward under the power of this rocket fuel. Okay, then it runs out of fuel. As it runs out of fuel, it will no longer be powered upward. Rather, it will just kind of go upward. Why does it keep going upward, by the way? After it runs out of fuel, the engine can't burn anymore. Why does it keep going upward? Jeremy? Yeah, it's moving, right? It's moving. It's moving at 200 meters per second. It's going to keep moving for a while. Now, it's going to slow down, and it's eventually going to stop, but not instantly. So it's being powered upwards in the blue, and then it's just kind of coasting upwards or gliding upwards in the green here. We know that at the end of the acceleration phase, okay, when it runs out of fuel, we're going to say VF is 200 meters per second. That makes VI for the green one 200 meters per second. It ends at 200 meters per second when the fuel runs out. It begins at 200 meters per second after the fuel runs out, when it begins to coast. For the green one, we're going to say A is neg 9.81. Not for blue, because it's being powered. There's forces other than gravity acting while it's being powered, while there's still fuel in the engine. It accelerates for 50 seconds. That's a time. Is that a blue time or a green time here? Yep. Sorry? Good. The blue time. We want to find the acceleration right here. We want to find the displacement in blue. Okay, how high does it go when the fuel runs out? We already talked about this, right? We already talked about why that happens. Oh, we have one more given. 20 seconds, that's going to be a green time, right? And we want to find the displacement up here. Let's do blue first. Okay, let's say, what would the initial velocity be of this rocket? What would the initial velocity be as it sits on the ground? Peyton? Right. So let's say A for blue is equal to delta V over delta T. It's 200 minus 0 over a time of 50 seconds, which gives me 4.0 meters per second squared. Okay, there's the acceleration. Let's say for the displacement, let's say for the height at which the fuel burns out, there's a couple of options here. Uh, 100 times 50 is 5,000. $5,000 meters or 55 kilometers. What's its max height? Let's solve for delta D up here. In green. Its initial velocity, that is during its gliding phase. Hold on one second, guys. Let's just finish this up, okay? Is 200 meters per second. Just hold on. Don't pack up, please. Times 20. Mrs. Donnelly and Rayanne Bordley, please see Mrs. Donnelly. We're going to get a number there for the displacement. That's not our answer. What do we have to do now to get our answer? Sam, last thing. Yeah, this is the displacement during the gliding phase. We want to find the maximum height above the ground. So we have to add that to the max height during the acceleration phase, right? So whatever we get in green there, added to the 5 kilometers, that's our maximum height above the ground. That's a tough question too, okay, when you combine all of that stuff. Okay, but it's a good question. Okay, it stretches our mind and makes us smarter. All right, if you had trouble with any of the other ones, then try them again tonight. Okay, maybe you can do them now. Ask me tomorrow if you have trouble, okay? We'll see you tomorrow, guys.